Hello, in this video we're in the weighted least squares regression setting, and we're going to estimate the error variance and derive its distributional properties. So as a reminder, model 1 is y equal to x beta plus epsilon, where the variance of epsilon is sigma squared v, where v is a known positive definite matrix. And the goal is we want to estimate sigma squared, develop an unbiased estimate for it, and then look at the distributional properties of our unbiased estimate. Now, an equivalent model is when we pre-multiply everything by v to the minus 1/2, and that's called it's a inverse of the square root matrix. And I have a video called Square Root Matrix if you're more interested in that, where v to the 1/2 is v, and then of course there's an inverse for v to the 1/2, which we'll call v to the minus 1/2. Now, generically, we're going to call that y star, and this x star, and this epsilon star. And then it turns out that when we pre-multiply, then the variance of the epsilon star is sigma squared I. And this model 2 is a model that we've spent the last almost 50 videos working in. And so, we could estimate sigma squared in this setting, or we could estimate sigma squared in this setting. And we would hope that they would be the same. Well, it turns out that they are the same, and we're going to show that. And let's just do that right here. So the residual in model 2, we'll work in model 2 first. I'd recommend previous videos 24, 27, 50, and 51 for background if it's needed for what we're getting ready to do. So the residual is, it's essentially we're taking this to the other side of the equal sign, but instead of the error variance, which is a population setting, we're in the sample setting. So we need an estimate for the x star beta hat, which is an estimate of this. So anyway, so this is the residual, the sample residual. And then here, so we can, this is commonly called y hat. It's the fitted value, fitted model. But y hat is the, if you pre-multiply y by the hat matrix, this is actually y hat. And then we can factor out a y star, and we're left with I minus h star y star. And this is the hat matrix for this in this setting. Now the expected value of the residual is, it goes into the y, and then the expected value of this is x star beta. But then this is 0. This is a perpendicular projection matrix onto the orthogonal complement space of the column space of x star. Or you could think of it as when you multiply the x in, you get x star, and then h star x star is just x, and so that's 0. Now let's look at the sum of squares residual, and it's also commonly called just sum of squares error. Let's look at the squared length of that residual, which is what the sum of squared residual is. So whenever you talk about length or orthogonality, you really need to ask the question, what inner product are we using to determine length or orthogonality? And in model 2, the inner product is the standard inner product, which is this, or the vector product sometimes it's called. And so this is the squared length of the residual vector. And then we plug in what we know about the residual, right? And then we transpose that in, we get this, right? But then y star is v to the minus 1/2 y, same way here. Now let's look at h star for a second. H star is the hat matrix in model 2 when it looks like this: x transpose x inverse x transpose. But now let's put in, each one of these x stars is v to the minus 1/2 x. So we put that in and we get this, and then this simplifies to that. Now if we look at what we know about the hat matrix in the weighted least squares regression setting, actually, which is this. This is exactly v to the minus 1/2 a v to the 1/2, right? So if a is this, so the v to the minus 1/2 is clearly this, and the a, which is this, but this needs to be a v to the inverse. So if we multiply it by the identity matrix, v to the minus 1/2 v to the 1/2, then that can be brought into, make it equal this, but we're left with the v to the 1/2. So h star can be represented like this. Now let's plug this in for the residual up here, right? And then we're left with this. So all we did was plug in what h star is equal to. Now, if we multiplied this in, now one thing, remember this transpose goes into this, so those reverse, and that's transpose. I is of course symmetric. And then when you bring this in, you get this, but then that cancels with this half, and we're left with this. Same way here, let's take this in, and we get this. Now, let's right factor out of v to the minus 1/2, left factor out of v to the minus 1/2, and then we're left with this. And then that's it. That's the sum of squares residual. Now let's develop that in the weighted least squares setting. So let's look at the residual in model 1. So again, it starts out very similar. The residual is y minus, the fitted value. But since we're in, and this is called y hat generically, but in the weighted least squares regression setting, we have an oblique projection matrix called A. So AY is actually y hat. And then when we right factor out of y, you get this. Videos 50 and 51 would be a good reference if this is a little vague to you. The playlist is Generalized Linear Models Regression. It's the 50 and 51st video in this playlist. So the expected value of this residual, that goes into the y, and that is x beta. But notice that ax is x, and then ix is x, so you get x minus x, which is 0. So the expected value of the sample residual in the weighted least squares regression setting is also 0. Now let's look at the variance of the residual. So this is a constant matrix, so it comes out front and then transposed out back, and then we just look at the variance of y. Now I have a video called Random Matrices or Vectors and Matrices that goes into detail about deriving these expected values in the multivariate setting and the variances in the multivariate setting. Well, this is sigma squared v, but the constant sigma squared can come out front and we're left with this. So this is the variance of our residual. Now let's look at the sum of squares residual, or SSE, in the weighted least squares regression setting. So we want to look at the length of the vector, the squared length. We're going to make reference to previous video 50 and 51 in our derivation here. But remember, when we're in the weighted least squares regression setting, we don't use the standard inner product for our inner product. We use what I have called the Mahalanobis distance. And that's actually what previous video 50 deals with. And so this is actually the squared distance in the weighted least squares regression setting. So we plug everything in. This is the residual, v to the inverse, and this is the residual. Now we simplify. So they take the transpose in, we get this. Well, we're done. That's it. That's the same as the same sum of squares residual that we got in model 2. So this is it. So they equal. So now let's derive an unbiased estimate for sigma squared. So we need to take the expected value of this sum of squares residual. Now remember, it doesn't matter if we're in model 1 or model 2, the sum of squares residual is the same. So let's look at it in this model since we're already here. Now the expected value of this quadratic form. Now I have a video called The Mean, the Variance of Quadratic Forms. if you need more detail on this step here. But this is equal to the trace of that middle matrix times the variance of this vector, right? And then it's plus the mean of this vector times the middle one times the mean. But the mean of the residual is 0, so this goes away, and we're left with this. Now the variance of the residual is this, and I don't know why there's a transpose there. It shouldn't be. So it's the variance of the residual, which is, so it's a trace of this product, which is this. Now what I do next is I multiply both these into this side, and we get this. Then we multiply this out, okay? So I times I times minus A, then this junk times I, which is this, and then this times A, which is this. Now, in previous video 52, we showed that AV transpose is just AV, and we're going to make use of that in this next step. So here, the trace of, you can think of it as the trace of each individual. And the nice thing about the trace matrix is you can move them around, but you have to do it in a way that's legal, mathematically legal. So if we take this to the back side, V to the inverse is I, so we're left with A. In the same way here, so V to the 1/2 AV, take it to the back side, we're left with A. So we have minus A plus A, they cancel, and we're left with just this. So now the trace is actually the trace of each matrix, so it's this. But the trace of A is still a little unclear to me at this point. So let's derive an expression for the trace of A. Now the trace of A, if we expand what A is this quantity here. Then we can take this to the backside and we're left with this. So the trace of this matrix, so it's the matrix generalized inverse and then that same matrix. Now, it would be nice that if we could show that this is idempotent, then we can do some more things with it. Then the trace is equal to the rank of this. Well, so let's take this times itself, which is what we're doing here, to show that it is idempotent. But now look at this, that we have a generalized inverse, the matrix times the generalized inverse times the matrix. And the definition of generalized inverse is actually just the matrix. So then we're left with this. So it is idempotent. So then this becomes the rank. The trace of this becomes the rank of this. And then what I'm getting ready to do here is if we look at the previous video 33 on the bottom of page 2, I go into much more detail about these derivations. And so if you want more detail, go to the previous video 33 in this playlist. So the rank of this is equal to the rank of just this matrix. And then this V to the n minus or inverse can be broken up into square root matrices. And then the rank of just half of it is this, and that's positive definite, so it's the rank of that. So now we have an expression for the trace of A. It's just the rank of X, so we can put it in there, right? So then we just say the rank of X. So now we have enough to develop an unbiased estimator for sigma squared. So if we take the expected value of the sum of squares residual divided by this constant, right, this constant. So then we take the expected value of this, we're just left with sigma squared. So it's an unbiased estimate. Now this piece in here is often called the mean square error. So the expected value of the mean square error is sigma squared. Now let's derive the distributional properties of this quantity here. Note that y star divided by sigma is multivariate normal with this mean and variance covariance matrix, the identity matrix. So then it makes what we do next much easier, since this is the identity matrix. But a few notes beforehand, that when you look at one of my videos called the distribution of quadratic forms, we're going to need these properties in that theorem, so that it is symmetric. So take that in. Well, this is symmetric and that's symmetric, so it has to be symmetric. It is idempotent because, you know, I is idempotent, H star is idempotent, so that it makes this idempotent. This quantity, which we call lambda, is 0 because I minus H star is a perpendicular projection matrix onto the orthogonal complement space of X star, right? Multiply that in, you get 0. The trace of H star is, if we put in what H star is, right, and then we can move this to the back side and we get this, and then we just showed that the trace of this is actually the rank of X. We just showed it on the previous page. Then that says if we let R be the rank of this symmetric idempotent matrix, it breaks, since it's idempotent, it's the trace, but then the trace, you break them up, and then that is n times the rank of X. Okay, so now we have enough background to just instantly say, using the distribution of quadratic forms, one of the theorems in there says that this quadratic form divided by sigma squared is a chi-squared with r degrees of freedom, a non-centrality parameter lambda, but the lambda we said was 0, so it's a central chi-squared with r degrees of freedom. And that's actually all I have for today's video. And deriving this distribution property in this video is going to make the next two videos easier, because I'll refer back to it. There we're going to derive it test for estimable functions, and then we're going to derive the partial f test in the weighted least squares regression setting. So I hope you enjoyed this. I sure did. Please like the video and subscribe so you don't miss the next one. Thanks. Bye.